So last time we learned the diode models. Okay, so let's go to the screen. And the first model we explored was the ideal model. Okay, in which it's either on or off, forward or reverse. Once the diode is forward, its voltage drop is zero, and the current can take any value from 0 up to infinity based on the circuit. If it's reverse, it's off, meaning that the current is always 0, the opposite. And the voltage can take any value from 0 to minus infinity because this is reverse. And again, the directions are very important. Okay, so we usually, for normal diodes, and I will explain why I call it normal diodes, we assume that the current is flowing from P to N, and it should be positive in forward and 0 in reverse. And so this is ID. And the voltage is from N, the opposite of the current, from N to P. And it should be 0 in forward for the ideal model, and negative in the reverse bias. Okay, then we said that maybe 10 or 20% of the problems we solve it using the ideal model. Then we explore more important one, which is the constant voltage model. And in that guy, we can look at it again as two regions. In the reverse bias, the current again is 0, just like the ideal model. And the voltage again is negative from 0 to minus infinity. But in forward, there are two regions, okay? Between 0 and 0.7, or whatever the on voltage, or the turn on voltage, or the built-in voltage of the diode, it's forward, but it's still off, because the diode needs 0.7 so that the current can change exponentially while the voltage is not changing so much. Okay, but once the input voltage of the circuit can afford the VD on, or the on voltage of the diode, which is 0.7 in most of the silicon diodes, then the diode will have a constant voltage of 0.7, not 0 like the ideal model. And again, the current can take any value from 0 up to infinity. And of course, positive. Okay. And we solved one circuit, which is this simple circuit on here. And, in between, I said that this is one of the applications of the diode. Okay. And actually, this is called a logic gate. So this is logic gate circuit. It's a circuit, okay, that do some logic. And I said that there are two kinds of circuits. There are analog circuits and digital circuits. Okay, in digital circuits, we usually you classify the voltages, especially the input and the output voltage of this circuit, into two categories, either low or high, based on the value. So for some ranges of the voltages, we say this is low voltage. And the symbol for any low voltage is 0. For some other range, which is higher, okay, we call the voltage is high voltage. Okay, and the symbol for a high voltage is 1. And for this particular circuit, which has 2 input and 1 output, we discovered based on our analysis, when we change the input voltages, and since they are 2, and we have only low or high voltage, okay, so we represent the low voltage as 0, and we represent the range of high voltages around 5. So if we change VA and VB between 0 and 5, so we'll have 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. Or as a voltage, 0, 0, 05 5055. And again, a high voltage usually represented by as a symbol as 1. And we found that based on the analysis by solving the circuit, we found that when the two inputs are 0 volt and 0 volt, the output is 0.7, which can be considered low. So this is also 0 if we represent it as a symbol. With 0 and 5, we get 0.7 again. With 5 and 0, we get 0.7 again. But with 5 and 5, we get 5. So if we, put a symbols for all these voltages, we have 0, 0 will give us 0. Low, low will give us low voltage. Low, high will give us low again. High, low will give us low again. High, high will give us high. Now, this is a digital circuit. Okay, it can be considered a digital circuit because the input voltages has only two values. Okay, either 0, which is low voltage, or 5, which is a high voltage. And we found that the output is either 0.7, which is the on voltage of the diode, or 5. And 0.7 can be considered low because I said there are, we usually have two ranges, a range for low voltages and range for high voltages. So 0.7 can be considered low. So this output can be only high under one condition, when the two input voltages are also high. Other than that, the output is low. Okay? And this is actually something called AND logic gate, or AND logic gate circuit, or logic circuit. Okay? So what is this AND that I, write it in capital letters, because it's not our AND that we use in text. Okay? So let's now go to our lecture again and, see what is this application is. Because some of you didn't take the digital circuit design course. So I will explain. You should take this logic gates in the digital designs. But since this is one of the application of the diode, I have to, give a highlight of this application, or digital circuits, we can say. So this AND gate or logic gate, based on its name, it does some logic. Okay, so it's imitating the logic that only human can do in this world. It's a simple logic, just one logic. Okay, that if you have some operation, some operation, okay, or some conditions, and based on these conditions, you're gonna do some action. So all the conditions must be satisfied in order to do the action. So let's do it in a very simple manner. If there is some operation that has two conditions, okay, two conditions, and these conditions can be either satisfied or not satisfied. So with AND logic, we are saying that the two conditions must be satisfied in order to do the action. If only one of them is satisfied, or both are not satisfied, I will not do the action. Okay? One application of that thinking or logic is can filling, something like this thing here. So basically you have a kind, of a build or something, okay? And you put your can on that build. And by the end of the line, you have a kind of tab. I don't know, I'm not a good drawer here, but I will try to do it. Okay, this is can or cans. built or a production line, part of a production line. Okay, and this is just tabs that tape that we know. Tab or tape should be with E. I'm very sorry, but anyways, that's not an English matter here. Okay, so now we want to control this tape here. We want to control it to fill the can. So we have two conditions. The first condition is that you must have a can underneath the tape. This one here. Okay. So condition one, you must have can just underneath the tape. If there is no can, why I should turn on the tape or whatever you call it, tab, whatever. Okay. The valve, call it whatever. Why I should fill something that is not there. The second condition, which is tricky, this guy here, this build should be moving. Because if it's not moving, if it's static, I will fill, and even there is a bottle there or a can there, I will fill just one of them and I will not fill the others. Only the first one will be filled, then board around, because you didn't turn off the tape, because it's just one can and you just fill it, okay, and you want to fill another one, and to do that, this this build should be moving. So this one will be go to another step in the production line to for example seal it or something. Then another one comes after, will be put instead of that one and be filled, go to the next step, and so on. So I don't know what they call, what are you calling that? So this build should be moving. Okay, so we have two conditions in order to open this tape. This is condition one and this is condition two. Both must be satisfied in order to turn on the tape or tab or whatever you call it. Okay, or the valve, or to fill the can. So we can do that using this is basically an AND logic. Okay, so let's have a circuit, something like so this our circuit here that we just explored or solved last time can do that for us. So this output here, let's do it with another color. So this output can control the tape. If VO is low, tape is off. If VO is high, tape is on or fill. VA can represent, we can put some sensor to detect if the build is moving or not. So this can be, for example, representing condition 2 or 1, and this can represent condition 2. So for example, VA, is an output of a sensor or a device, whatever. We don't need the details here, okay? Of a circuit that detect if there is a bottle or not. If there is a bottle, it will be high, 5 volt. If there is no bottle, it will be 0. And V or VB, another output for another circuit that detects if the build is moving or not. Okay, if the production line is, you know, is not halted or not paused or something. And if the belt is moving, then we are sure that if we fill the first can, we will fill the next, and so on and so forth. And if it's moving, you know, VB will be high or 5 volt. If it's not moving, it will be 0. So if this is 1 or 5, if this is 1 as a symbol for high voltage, let's call it high, which in that case 5 volt. Then this guy will also be high and will, I'm sorry, yeah, not that, will turn on the tape, and you know, you can fill the can or the bottle. Okay, if any one of those is low, either this one or this one or both, then this guy will be off, will be low, and the tape will be off. Okay, so this is called AND logic, and luckily we could design a circuit using our diode to do that logic for us. Okay, we don't need a guy that stands there to watch if the belt is moving and, you know, if there is cans or not, so he can turn on or off the tape for us. Just a circuit, and you don't need any human, because this circuit can do the logic for you. Okay, so this is one of the logics that we can do using circuits, and this is one of its applications. Now, okay, you guys now get the idea of logic gates and logic circuits. It's just a circuit, okay, that have an output. This output can be high or low, and also the input which controls or determines the output of the circuit also can be high voltage or low voltage. And usually this high voltage is a range around 5, usually, not so all the time, and or most of the famous applications. And the low is usually a voltage around 0. Okay, I will do now the same circuit again, okay, but using the ideal model. It will be the same, there is no much difference, but although of course we need now the other model to do that, which is the ideal model. Okay, so let's do the same or solve the circuit again using the ideal model. So let's use our, you know, so we have the first case when A or VA and VB both equal to 0. Okay, so if we put 0, 0 here, then again we can ask ourselves the question, okay, if DA or DB is on or off. Since they are identical branches and we have identical voltages, then you know by your, you know, smartness that they will both on or both off, both forward or both reverse. Same operating point. So in that case here, the B is closer to a 5 volt, the N is closer to 0 volt, so it's probably forward and on. Okay, so assume DA and DB both forward or on directly. Okay, so VDA equal to VDB equal to 0, because we are dealing with the ideal model now. So once they are on, or once you assume they are on, the voltages are 0. It's a drop, so there's no drop here, can say, on either VDA or VDB. And since there is no drop, so V output will be also 0, because there is no voltage difference, right? Or you can make it in more detail. For example, VDA here is equal to VO minus VA. So equal to VO is unknown for us, VA is known, is 0. So VO is equal to 0. And you can do the same using the other branch. It will be VO minus VB. Again, VO minus 0, so VO is equal to 0. Good. Now let's calculate the current, because this is our check if they are really on or off, or forward or reverse. And we know the current should be positive in order for this assumption, so that assumption to be true, or right, or correct. So this is IB, this is IA, and this is Mr. I. So I is equal to VO minus 5 volts over the resistance, which is 1 ohm, I think. So this guy will be, oh, I'm sorry. The current should be the opposite way. I'm very sorry. You know why it should be in the opposite way or not? Anybody can give me an answer, because if you don't know that, then it will be a very big problem. Why the current should be moving upward, not downward? I will not give up on that. So anybody knows why the current should be going up? Boom. You can write in the chat.
We're
Yes.
dealing with conventional current rather than the other model.
No, I'm talking about that guy here, that current here. Why it should be going up in that way?
Because it's coming from the source and going out.
Of course, because basically, you know now this guy is 0, and this is the higher voltage, then the current should be going in that way. Then it will be branched to IB or VDB or DB and DA. And we know also that this guy, when it conducts or on, the current should be flowing in that way. The same, of course, for that diode as well. So if this is moving in that way and this is also moving in that way, so the source itself should be moving in that way. So to entering the node, then branch. So guys, please, try to solve a lot of examples. I will do my best with you. I hope so. But try to solve many examples, because if you didn't get the notion of solving a circuit, it will be a very big problem in the exam. Okay, so you have in the book, okay, you have many examples after chapter 3, I think. Yeah, such chapter 3. Yeah. You have many examples, huge number of examples, okay, that you can solve, because if you didn't do that, and you just, chapter 3. And you just, solve the homework. The homework is usually, one problem or two. This will not help. Okay? So you should do some extra work by yourself. But I will try to do many, circuits with you. But anyways, so the current I in that way, okay? So it's equal to the opposite now. 5 minus VO. 5 minus VO. So 5 minus 0 over 1. So this is 5 amps. Okay. Then since DA and DB are identical, you will say this in the problem definition or given in the given, since they are identical, and these both have the same inputs. With both inputs, okay. So the branches are identical. Are identical as well. So I equal to IA plus IB, but IA is equal to IB now. So both is equal to I over 2, 2.5 amps, positive and flowing in that direction. One may say, okay, if the direction of the current was not given in the problem, okay, and I assume it in that way, I like to do something in a difficult manner, and I assumed it in that way with the red arrows like this. Is that wrong? No, it's not wrong at all. But you must, with these new arrows or new directions, you must get negatives here. And with the negative number with these directions, then the assumption is correct as well, because negative in that direction means positive in the opposite direction, so it's still flowing from P to N. So that's right. You are on the right path. Okay. So since they are positive, then this assumption is correct. Now one may say, okay, both with 0, 0, the output, so let's write it in another color, the output is equal to 0. Although when we solve with the practical constant voltage model or the practical model, we can say, because it's more practical to use, the output was 0.7, not 0. Is there a difference? Yes, there is a difference, of course. Okay, but if this is a logic circuit, okay, and you just want to know it's a high voltage or low voltage, okay, and remember 0.7 was considered low, so this is also low. Okay, so that's why we may use the ideal model, which is not that accurate like the practical model or the constant voltage model. Okay, but at the same time we get to the same conclusions, although the numbers are different, because of course 0 is different from 0.7. Okay, so that's why we may use the ideal model, and we are still safe. We are still getting the same conclusions, no problem. Okay, so this is one example why we can use the ideal model without any problem. In the exam, until otherwise noted, or if I didn't mention explicitly use the ideal model or the the accurate model, which is just the exponential one, use the constant voltage model. So the constant voltage model is our default. Okay, which have 6.7. If I said use ideal model, then you must use the ideal model. Or as if I say solve it accurately or with the accurate exponential model, you must use the accurate exponential model. Okay. Okay, so let's continue with number B or number 2. If VA is equal to 0, but VB now is equal to 5. Solve that using, or let's do the 5 and 5. Okay, because again, this will ease out the other the last two states for the inputs. So we discovered that with both inputs are 0, that both were on. Okay, so let's now do something different. With both inputs are 5, so 5 here and 5 here. And let's see. So with this inputs here, we have B is closer to 5 and N is closer to 5 as well. So maybe it's off. Okay, but we're not sure if it's reverse or forward. Okay, it may be just in between. This point as 0, 0, this one here. This point, wow. This point, or even this, if it's a practical model, it is something between on or off. It belongs to both. Okay. But we know the characteristics that VD is 0 and ID is 0 as well. So it's something in between. You can't say to which it belongs. Okay. So we are not sure. So we're gonna assume it's off, and we're gonna see. If it's the wrong assumption, we can assume another assumption. So assume dA and dB off. Let's see. If they are off, the voltage is not known, because if they are off, the voltage may be 0 until to minus infinity. We don't know exactly, but we know it should be 0 or negative. But we know the current. The current, since it's off, the current, both current IA and IB should be zeros. So I as well is 0, because it's equal to IB plus IA. Good, but I is equal to 5 minus VO over R. So this is equal to 0, R is 1. So VO from this is equal to what? Is equal to 5 volts. Good. We got that guy here. It's equal to 5. Now we want to check if we are right or wrong. Just do the voltage drop. VDA is equal to the voltage on the B minus the voltage on the N. Okay, so the voltage VDA, the voltage here is VO, the voltage here is 5. So VA or VDB or whatever you start with is equal to VO minus VB. So 5 minus 5 is equal to 0. And VDA, VO minus VA, again 5 minus 5 is equal to 0. And that's proves that we are correct. Our assumption is correct. And the diode is basically with the ideal model is basically working, in that point here, just in between. Okay, at that point the voltage drop is 0, which what we got here, and the current is also 0. So we are fine. Nothing contradicts. Okay. So with this assumption, we found that VO is equal to 5. And one note here, with these two zeros, both diodes were on. With these two are 5, both diodes are off. So looks like we know now the conditions that makes which one is on and which one is off. So when we assume number 3, for example, VA is equal to 0 and VB is equal to 5, we can, assume a very good, because now they are not identical branches anymore, because both diodes has different voltages, inputs. But we know from 1 and 2 that we can assume that DA is on, because it has 0 as input, and DB can be assumed as off. And that's actually the correct assumption. If it's not correct, but you can, of course, assume another assumption. So let's do the calculations. If DA is on, we know the voltage VDA, the voltage drop should be 0. But the current IA should be larger than or equal to 0. If DB is off, we know the current must be 0. But the voltage, VDB is less than or equal to 0. 0 or negative. So let's continue solving that. So VDA is equal to VO minus VA. VO is unknown for us. VA is known, equal to 0. So VO is equal to 0. I is equal to IA plus IB. IB is 0 based on our assumption. So that equals to only IA. And I is equal to 5 minus VO over 1 ohm. So this is basically, and VO is equal to 0. We just got it now. So it's equal to 5 amps, equal to IA. And that's the first check that, yes, the current for the diodes that we assumed on is positive. That's very good. Now let's check for the other diode. Let's calculate VDB. VDB is equal to VO minus VB. VO is equal to 0. And VB is equal to the input, 5 volt. So this guy is equal to minus 5. Wow. So it was reverse. That's right. It was reverse even. And of course, if the diode is reverse, no current will flow. Okay. So our assumption is correct. Now, when you do the last one, actually you don't need to solve anything because it's there are very many high similarity in that problem. So when you assume the opposite, that VB is equal to 0 this time and VA is equal to 5, just to do the opposite of this. Okay, so basically DB is the one that will be on, DA is the one that will be off. You will find that I equal to IB equal to 5 amps. You will find that this is positive, and so the assumption for DB at least is correct. Then VDA and you will find that VO is equal to 0. Okay. And VDA will be equal to 0 minus 5. It will be minus 5, which is also correct because this will turn the diode into the reverse region, and in reverse the current is 0 as assumed in the beginning. Okay. So now let's draw our conclusions here. With this one, VO is equal to 0. With this one, we found that VO is equal to 0. Then we can write this table, this nice table here with VA and VB and V out. With 0 voltages, we got 0 volt. With 0 and 5, we got 0 volt again. This one here. I'm sorry, this one. And with 5 and 0, we got 0. This one here. And with 5 and 5, we got what? We got 5. This case here. If we write this, using the symbols high or low or 1 or 0. So again, with A, B, and O, the output, we like to do that in that way without voltages because this is now symbols, not real voltages. So 0, 0 will equal to 0. 0 and 5 is 0. I'm sorry, 0 and 1. I'm very sorry. 1 high and low will give us low. High and high will give us high. What is this? This is AND logic gate in nature, how it's constructed. Because of course, when you study digital design, you will not go into the circuit details. You will take the AND logic gate with a symbol by itself. So this is the symbol for the AND gate is usually something like this. A, B, the O, the output. It's a symbol. So this symbol here is for the circuit. There is something inside. What's inside? Something like the circuit that we see. We just analyze. Okay, guys, any question on that? I can explain from the beginning if you want. If you miss anything, you can say, hey, Dr. Mustafa, I cannot understand. You are just, saying nonsense. Any question? Don't be shy. The power supply is at the bottom. Troy, what do you mean by this? I can't understand you. Yeah, the power supply is at the bottom. The problem is it's 5 volt. Troy.
He was answering your previous question.
Okay. Oh, I'm sorry. Okay. Okay. Yes. Thank you anyway. Okay, guys, so let's take another example. Okay. So this one, we have two differences here. So in here, the source is 0. There is no source, we can say. There is no battery here in the bottom. It's just a ground. And now the sources for this circuit is actually the two inputs, V and VB. This is another logic gate, okay? Another logic gate. So we're gonna do that. I will do 2, or maybe let you to do the other 2, okay? But let's do that together now. Okay, so again, explore the output, okay, with all possible combinations of the inputs. The inputs can take 0 or 5. This will be, explained in a problem. So don't be, scared of that. So let's do that. So let's have the first VA is equal to VB equal to 0. Okay, so 0 is here. Can anybody guess what will be a correct or a smart assumption for the situation of DA and DB? Either on or
It's
off?
an OR gate now.
Yes, that's an OR gate. Yeah, that's right. Yes. And for those of you that don't know OR gate or didn't take digital design course, I will explain it at the end. But in that case, DA and DB will be on or off? Chris.
What was that?
Yeah. What will be the situation or the condition for A and B, the diodes? Are they on or off when I put 0 and 0?
They're both not conducting.
Yes. And basically to conduct, you need a source, right? And remember, there is no source here. So everything is grounded. So from where you will get a current, okay? These circuits are just, in some sense, they are passive. They need a source in order to give you a current, okay? So basically here, both diodes are off. There is no source. There is no need for analysis even, or what is B and what is A. Okay, so you can do that as well, but there are, a simpler reason why there is no current. So in here, you can do the old way that, B is closer to 0, N is closer to another 0, and the same for B, and both are, identical branches. So assume here that both are off. Good. And if they are both off, IA is equal to IB is equal to 0. And let's put the currents with proper directions. And now this current will be going down because the sources now are both A and B. There is no source in the bottom. Good. So let's, continue the solution here. So both are off, okay, and yeah. So I, which is equal to IA plus IB, is equal to 0 as well. I is equal to VO minus 0 over R. So VO is equal to 0. And now VDA is equal to VDB equal to 0 as well. So the voltage drop on the diode is 0. And that's 100% valid. And you know, matches our assumption that they are off. Because the diodes can have a voltage drop of 0 and current of 0. Because this is the point just between the reverse and forward. Okay, so with this guy here, the output is 0. Now, and the diodes are off. Now let's take another one, VA equal to VB equal to 5 this time. Oh, now we have 5 there. Let's do that with another color. 5. Forget about the last one now. So B is closer to 5. B again is closer to 5. Both ends are closer to 0. So we can assume that both are on. So VDA equal to VDB equal to 0 because this is ideal model. We are still, I'm sorry, let's do it with practical models. That's better. So I just gave you the harder one, the easier way, which is solving using the ideal model. But I will do all the examples from now on using the practical model or the constant voltage model. And in the exam again, or the assignment or whatever, you know, even in practical life, you should use the constant voltage model. Okay. But I will, if I want you to do with another model, I will tell you to do that explicitly in the exam or the homework. Okay. So we have VDA equal to VDB equal to 0.7. VDA is equal to VA minus VO. The voltage on that one, on B minus the voltage on N. So VDA is equal to 0.7. VA is known equal to 5 and VO is not known. From that, VO is equal to 4.3 volt. And you can verify with VB because VDB is equal to VB minus VO. If the assumption is correct, they should give you the same voltage drop or the same V output, of course, because it's just a single point and it cannot have two voltages. It should have only one voltage. So this is equal to 0.75 minus VO. Again, VO is equal to 4. This is just for checking. This is for checking that you are on the right path. Okay. Now the current I is equal to VO minus 0 over R equal to 4.3 minus 0 over 1, 4.3 amps. And this is equal to IA plus IB. And again, since they are identical, you know, and matches and they have the same inputs, so they are both equal. So this is equal to IA to IA. 2IA equal to 2IB. So IA equal to IB equal to 2.15 amps. Positive. Okay, so the assumption is correct. Let's do number 3 now. So let's write first the conclusion before going forward. So with that example here, we found that VO equal to 4.3, which is a high voltage. With high and high, we got high. Okay? And the diodes are on. Both are on. Now you guys do, I will choose some of you, okay, to give me the answer. I will do, so you will do that. VA is equal to 0 and VB is equal to 5. Okay, let's see. Let's see if this is right or wrong. I don't know. I will solve it with you. I have the solution in the notebook, but I will not look at it. So let's do that. So from A and B, we discovered that when we have 5s, we have on. When we have 0, we have off. So basically, I will assume that A or DA is off and DB is on. So it looks like you are in the right path, because if DB is on, then VDB is equal to 0.7. Okay. And if DA is off, IA is equal to 0. Good. VDB is equal to, let's see, VDB is in that way, so it's equal this minus this. VB minus VO. VO is not known, but VB is known as 5. So VO is equal to 4.3. That's right. That's right. That's right. Okay. Now let's calculate the current. Okay. The I is equal to VO minus 0 over R. So 4.3 minus 0 over 1, 4.3 amps. This is equal to IA plus IB. IA is 0, so IB is equal to 4.3 amps. That's also right. Now VDA. VDA is equal to VA minus VO. VA is 0. VO is 4.3, so you messed up with this. Minus 4.0. And that's right, because we assumed it's off and we got a negative voltage, which means it was reverse. So the current is really 0. So what is the problem now with your solution with VDA? What you have done wrong with that? Why you get it as 0?
I just assumed that nothing was passing over it because the diode was off.
Yes, it's off. Then okay, let's draw the graph or the characteristic to know what's really happening when a diode is off. So this is our VA, our VD in general, and ID with constant voltage model. The characteristic is like this. If a diode is off, that means its operating point is lying on that line here, from that point to on that line. Let me draw it. All of that are off. Okay. But you know that the current is 0. So when you assume a diode is off, so you certainly have a 0 current flowing through that diode. So that's what we did. We assume that IA is equal to 0. Okay. But you don't know the voltage. So the voltage will be determined based on the circuit analysis. So you complete your circuit solution or analysis, then you get VDA in that way. Any voltage drop, okay, with the arrow like this, from here to here, this is the voltage. This voltage drop is equal to that voltage, that point voltage minus that node voltage or point voltage. Okay. We know the voltage of that point, which is VA. We know the voltage of that point, which is VB. So you can determine the voltage drop and you can determine VDA. And it should be something less than 0.7. Okay, so this should be less than 0.7 in order to say, yeah, that's off. It can be 0.3, for example. It's positive. But you see, 0.3 is actually here. It's before 0.7. It can be here. It can be anywhere on that horizontal line, horizontal red line. All these points, okay, have the same characteristic for the diode, that the diode in all these points is off. Its current is 0. But the voltage can take any value based on the circuit. Okay, that's good. And of course, so with that one here, so this was wrong, and that's right. The output is 4.3, and number 4 will be the same. VA is equal to 5, VB is equal to 0, then VO will be equal to 4.3. Now let's do the table again and see what's difference. VA, VB, and VO. 0, 0. This gives us 0 here. Oh, yeah, 0. 0, 5, 4.3. 5 and 0, 4.3. 5 and 5. This is give us also 4.3. As symbols, low, 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 high, 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 low, high, 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 high. Okay. So now this is another logic. This is called OR logic, in which if any condition is satisfied, then do the action. Of course, if both are satisfied, also do the action. In the end, logic, both must be satisfied in order to do the action. So only the last output here with 1, 1, when both conditions are satisfied, is 1. But here, no. You have some process, okay, and you want to take some, this process has many conditions, and you want to take some action. So you're going to take your action if at least one of the conditions, even if they are million, if one of them is satisfied, you take the action. At least one. Of course, if 2 out of million, that's more good, better. So you do the action. 3, if all of them, the whole million is condition are satisfied, do the action. But if any of them is not satisfied, then don't do anything. Don't do the action. The output will be 0. And just think about applications for this. It's obviously not the can filling. It is something else, some other example. So just look around. There are many, if you go to, for example, if you go to the airport, if you have the state ID, you can fly. If you have a passport, you can fly. If you have the driving license, you can fly. But if you don't have any ID in one of those, you will not fly. They will not let you in, right? So this is an example for the or condition or logic. I'm sorry, or logic. Okay. So this is OR logic circuit. Good. So let's take another example. We have many examples today, which is really nice. You should be happy for that. Why I'm doing that? Because when you try to solve yourself, there are many examples. Again, you will not do good in the exam, or I'm not making you scared or something, but you must be trained well. You must train yourself well in order to become fluent in such kind of circuits. So this is not a normal circuits, because we added some, new device which is called the diode. So we need some special, you know, analysis because of that new comer, can say, arrival of device. Okay. So yeah, let's do that. So there are two very simple for this circuit here with these currents. You know, you should, you know, conform all the time with the currents givens. If it gives you the current, for example, in that way here, you should solve the problem with that way. Don't assume in the other way. Okay. If it's not mentioned, what is the current direction, you know what to do. Assume always that the current in the diode flowing from B to N and the voltage is the opposite, just like a resistor. So let's solve that. We have here 4 diodes. It become more complicated now. Really complicated. You can't do the smart like you can do, but as the number of diodes increases more and more in your circuit, it's really hard to trace and make an intelligent guess about what should be the good assumption. You know, because if your assumption is wrong, then you must, you know, redo everything, assume another assumption until you get some, you know, matched results to your assumption. Okay, there's no discrepancy at all. So now let's look at one by one and see. Okay, so those guys here, okay, their N, so D3 and D4, their N are closer to 2. That's for sure. But there B, you know, we have here 5, we have here 5, we have here 2. So you can't say, you know, if this branch here is not there, I mean you have only the circuit is only that branch, you will say that they are on or they are forward. But with this branch in here, that guy here, you know, it's really difficult. Really difficult. And the same for these two as well. So with that being said, just assume all of them are on. So and see. Again, if you get some discrepancy, you'll go back, you know, and try another assumption. Okay, so let's assume, so let's write this down, that it is really hard to make an intelligent guess. It's really hard. And that is the main purpose of that example, to show you what to do when you have many diodes in the circuit. Okay. So assume that all or D1, D2, D3, and D4 are on. All on. If all on, then VD1 equal to VD2 equal to VD3 equal to VD4 equal to 0.7 volt. I need now the notebook because we have many numbers and calculations here. Yes. Okay. So we have 0.7. That guy have 0.7. That guy also have 0.7. 0.7 and 0.7. And of course, to check, after we solve the currents in the diodes, I1, I2, and I3 should all be positive. Let's see. Okay, so let's do that. At this node here, I1 is entering the node. I is entering the node. I1, I2, I3, all are going out of the node. So I is equal to I1 plus I2 plus I3. Okay. I is equal to this current here, this guy here, is equal to 5 minus VO over 1 kilo ohm. 5 minus VO, VO is not known, divided by 1 kilo ohm. I1, which is that guy here, well, that's a little tricky here, okay? It's flowing in that branch. So if we assume that this is called A, so this is also I1, right? Because this resistor is in series with D1. So the same current is flowing in both. So I1 can be said to be as VA minus 5 over again 1 kilo ohm. I2 is the same. Just name this node B. This is VB minus 2 volt. This is 2, not 5. Over 1 kilo ohm plus I3, which is that guy here. So let's call this C. It's equal to, so I3 is equal to VO minus VC over, this is again 1 kilo ohm, just for good. And this is 1 kilo ohm. Over again 1 kilo ohm. It's a good thing here that, you know, all these are equal, so we can just remove them by each other. Now, what is VA, what is VB, and what is VC? So let's start by the easiest one, C. Okay, so we know that from this point in here, this point has a voltage sources of 2. This guy is unknown, but we know that these, based on our assumptions, that these 2 diodes, 3 and 4, are on. And this is the direction of this 0.7. So VC is actually equal to 0.7 plus 0.7 plus 2. And this will be equal to 3.4 volt. That's obvious because the voltage drop combined of these 2 diodes are 1.4. That means that point here has a voltage greater than 2 by 1.4. So if this is 2, so this should be 3.4. So that's 3.4 minus 2 is equal to 1.4, the voltage drop on the 2 diodes together. That's VC. Now VA. We know that, let's do VB first. VB, because it's clearer. VB is 0.7. I'm sorry, VD2 is 0.7. The voltage drop on D2 is 0.7. That means this node, which is VO, is greater than this node, which is VB, by 0.7. So VD2 is equal to, the voltage drop on diode 2 is equal to VO minus VB. So VO is equal to, or VB, I'm sorry, VB is equal to VO minus 0.7. It's not known yet, but it has a relation to VO. The same is said for VA. If this is on, as based on our assumption, this should be larger than this by 0.7. So V1 or VD1 is equal to, again, VO minus VA this time. So VA again is equal to VO minus 0.7. So we take these two equations and remove VA from here and VB and put instead their equivalents. If you do that, you will find yourself with this equation. 5 minus VO is equal to VO minus 0.7 minus 5 plus VO minus 0.7, which is VB, minus 2 plus VO minus 3.4. This equation has only one unknown, which is VO. And based on that equation, VO is equal to what? 4.2 volts. Good. Then now we didn't make any check. We will do now by calculating the currents. So let's start by I. Mr. I. Mr. I is equal to 5 minus VO over 1 kilo. This can be determined very easily. So I is equal to 5 minus VO over 1 kilo ohm. So 5 minus 4.2 over 1 kilo. This is 0.8 amps. Good. Okay. Now, I1, which is flowing in D1. I1 is equal to this one here, VA minus 5 over 1 kilo. VA is equal to VO minus 0.7. But VO is known now, 4.2 minus 0.7 minus 5. What is all of that? So this is minus 5.7, 4.2. This guy minus this guy is actually minus 1.5. Is that correct? No, this is not conforms or not matched to our assumptions that D1 is on. But let's continue. I2 is equal to VB minus 2 over 1 kilo ohm. VB minus 2 over 1 kilo ohm. This is I2. Equal to VB is again VO minus 0.7 minus 0.2, 1 kilo ohm. VO is 4.2 minus 0.7 minus 2 over 1 kilo ohm. This is equal to, this is minus 2.7. And here is 4.2. This will give us what? Let's do that very quick. Yeah, whatever. It's 4.2 minus 2.7. So let's forget this one. So 2, and here is minus 1 plus 1.5 amps. That's conform with the assumption. Now I3 is equal to VO minus VC over 1 kilo ohm again. VO is 4.2. VC is what? VC is what? 3.4 over 1 kilo ohms. This is positive. That's good news. Okay, 4 minus 3 is 1. Yeah, it's 0.8 amps, which is positive again. So one current of the currents that we calculated in the diodes is negative. Of course, that destroys everything. Only one mismatch. So the assumption is wrong. But now we must assume another assumption, of course, to get the correct answers. These are not the correct answers. But based on that, analysis, we can have an idea which is on and which is off. it's not, you know, a foolproof or, you know, a definite assumption, but we can assume the opposite of that. So since I2 and I3 got positive currents, we can assume that D2 and D2, which is that one, and D3 and D4, which have positive currents, based on that, you know, wrong answer, by the way, we can assume they are on. And we can assume that the diode that we got negative currents that flowing through it off in the next time, the next assumption. That may be closer to the good answer. Maybe it's not, you know, it's not proved yet. We should prove or disprove again. Okay, it's not a definitive. It's just, you know, again, some smart guess. Okay, so let's assume that all are on except D1. So this assumption now is incorrect. The assumption is incorrect. So we didn't solve the question yet. We're still struggling with A, finding VO. So let's assume another assumption. Assume that D1 is off, D2, D3, D4 are on. D1 is off, that means I1 is 0. D2, 3, 4 are on, means that VD2 equal to VD3 equal to VD4 equal to 0.7. The analysis will be simpler now because one of them has 0 current. So this very long equation here will be reduced a lot, this one here, or this one. Will be reduced a lot because one of the variables or the unknowns is now known, which is the current. So with this assumed, we can say that I equal to, again, I1 plus I2 plus I3, but since I1 is 0 because it's off, so this is equal to I2 plus I3. So 5 minus VO over 1 kilo equal to VB minus 2 over 1 kilo plus VO minus VC over 1 kilo. VC again, since you assume that D3 and D4 are on, again is 3.4, so it's known. Again, VB is equal to VO minus 0.7 because you assumed again that D2 is on. So this will lead to 5 minus VO equal to VO minus 0.7 minus 2 plus VO minus 3.4. Again, these 1 kilos will go away. And based on that, if you do that assumption and, you know, do the analysis, you will find that I is equal to 1.3 milliamps. I2 is equal to 1 milliamps. I3 is equal to 0.3 milliamps. And I4 from the beginning, I1, sorry, is equal to 0 from the beginning because D1 is off, assumed off. But now we have some, you know, matched results because, you know, you assume that D2 and D3 are on and you got positive currents through them, which is really good. Now, let's calculate VDA, oh, I'm sorry, VD1, so that we can know if our assumptions that D1 is on or off is right or wrong. Very good. You know that VDA, or I'm sorry, VD1 is equal to VA minus VO. Okay. You know that I1, which is 0, is equal to VA minus 5 over 1 kilo ohm. So just multiply by 1 kilo ohm, the zero will be 0. So VA is equal to 5 volts. 5 volts. So VD1 is equal to VA, which is 5, minus VO, it's VDA or the other one. I'm sorry, VO minus VA. I'm very sorry. VO minus VA. Yeah. VO minus VA. And VO is, we didn't write it. So VO, if you do the calculations, you will find that VO is equal to 3.7 volts. And based on VO, you can calculate, all the currents. This is R. Okay. So VD1 is equal to VO, which is 3.7, minus VA, which is 5. This is what? This is minus 1.3 volts. And this matched what you assumed, because you assumed that V or D1 is off. That means it's reverse, or its voltage is less than positive, but less than 0.7. And now, let's go back to the circuit again. We have a trick here. You know, we have something to say. But this is not based on forward or reverse. This is based on the sources, the batteries that you have in your circuit. So we have here, 4 batteries. 2 of them with 2 volt and 2 of them with 5 volt. Higher values, okay? Usually, okay, when you have a higher battery in the and a smaller battery voltage in the same circuit, usually maybe the higher battery will charge the lower battery voltages, or the batteries with lower voltage, and that means that the higher voltage battery will have its current will going out of it, and the lower ones will have a current flowing into the positive terminal. Okay, so let's draw the same circuit, but with with more visibility on the batteries. So this guy here is a battery just like this. This guy is another battery just like this. This guy is another battery just like this, and this guy is another battery just like this. So these two has higher voltages. They are charging other batteries, maybe, and those guys are with lower voltage, so they are charging. I'm sorry, they take a charge. Okay. So the current is flowing into the positive terminal. But wait a minute here. If this guy, this 5 volt, is charging other batteries, that means the current is flowing out. And it must be positive, of course, if it's really charging other batteries. But diodes cannot permit current flowing in that way. The current of the diode is either flowing in that way and positive or 0. You can't find a diode, okay, with a current flowing from N to B in that way. Of course, if it's Zener diode, if you remember the Zener diode, or is a normal diode in breakdown, yes. But for our analysis here, usually we assume that there will be no breakdown will occur. Okay. So this battery here cannot charge other batteries because there is a diode in between within terminal closer to the positive terminal of the battery. And since it has a high value, it doesn't need to be charged from other batteries, right? So it's really a good guess in the beginning, but I didn't mention that because I intended to have an incorrect assumption to disprove it and have a correct assumption. You can, from the first glance, when we just start to solve the problem, that you can have such kind of of guess that the higher battery like this one 5 cannot charge other batteries because there is a diode here with such polarity. So the current cannot go out of the positive terminal. So it may be good to assume that this guy, which is D1, is off. But these 3 diodes here, okay, they are connected to lower voltage batteries, so they can accept a charge from higher battery voltages like this one. Because if they are charged right now, okay, or accepting a charge, the current flow will flow in that way, or in that way, and the diodes can allow currents flowing in that way. But even if you just some deep understanding of what you are seeing in the problem, and of course that can reduce the time to take to solve any problem or such kind of problem. Okay. But again, if you didn't have such idea or such deep understanding, or you're charging, discharging, and such stuff, you can assume all of them are on, and then based on your result, you can go back. The guys with positive current can be assumed on. The guys with negative current can be assumed off. Then you solve again. This is not again, this is a smart guess, but it may not be true. That's fine. And keep going in that until you find a matched results. Okay, just a very small question here. If you're gonna just go blindly, okay, and assume on and off for each diode here, how many or what is the maximum number of assumptions that you can have? In the worst case, how many times you have to solve the problem in order to get, yes, 16, that's right, yes, 16, okay? So basically you have each diode, D1, D2, D3, and D4, okay? Then let's assume all on, then all on except, for example, D4, all on except D3, and you continue until or off. Each diode has 2 states or 2 conditions, on or off. Since you have 4, you have 2 to the power 4, which is equal to 16. So if you just go blindly and you are really, really unlucky guy, so you have to solve the problem 16 times. So having, some smartness about the problem is really, a good thing. Okay. So let's continue, with another really nice example. Any questions so far? Anything is not digestible or something, Everything is clear? No questions? Okay. So let's continue here. So for that particular problem, okay, we have here also a very simple circuit, just one diode, but the diode is connected in parallel to a resistor, which is R1 in that case, okay? And we know that the diode needs 0.7 in order to conduct. And to conduct, again, the current should be flowing from P to N and positive value. Good. Before going into the details of that, what's really required, if we make like, just on the side like this, if the input, for example, is equal to 0.4 volt, what do you guys expect for the diode? Is it on or off, reverse, forward? What's your expectation? Off, that's right. Yeah. Can you explain why, Troy? Can you explain why, any of you, Arsenio or Troy? Yes, that's right. Because the voltage across the diode at that time will be less than 0.7. Because the diode, again, cannot create this 0.7 by itself. It needs a source. So the source needs to be at least 0.7 in order to say or guess that the diode is on or off. So to turn the diode on or off, okay, the input or the input voltage must at least be with some value that is, enough to turn the diode on or off. Now let's ask another question. If the input is 0.8, it's slightly larger than 0.7. What do you expect? So Arsenio expecting it will be on. Okay. Let me go with Arsenio. If I say that R1 is equal to 0, short circuit, is it still on? Arsenio, you said that the input is with 0.8 at input, but you said it will be on, okay? Or maybe on. Now if R1 is 0, it's just shorted, okay? What will be the voltage across the diode in that case? Guys, if you have a short circuit like this, what is the voltage difference? 0, yes. Someone should speak, okay? It will be 0. And if the diode has a VD of 0, because the voltage drop on the diode, on the resistor, which is short circuit here, is exactly the voltage drop on they are parallel on the diode. And if the diode is shorted, then it's off. Basically, the current that's flowing in that way, all of it will go to the short circuit. So the current in the diode will be 0. It's off. So now, it's not only the input voltage value that matters. The input voltage value and also the diode, the resistor that is in parallel with the diode. Because when this resistor was 0, then the diode couldn't conduct as well. Okay, so here the diode is off. It's also off here. So we are expecting now that if we calculate this, as in A said, in A he said that find the minimum input that will turn the diode on. Since, you know, with this, you know, very basic analysis, we discovered that it's not only the input, it's also the resistor across the diode. I'm sorry, in parallel with the diode. Then we are expecting when we solve this question or find this minimum input voltage, okay, we are expecting that this input minimum should be also function of the resistors. Okay, so let's do that. So let's solve A and C. When it says that find the minimum input that will turn the diode on, that means if we draw the characteristics like this, since it will turn, you know, it is the minimum input, then the diode will be working at that point. So this is the operating point when Vn is equal to V input minimum. The minimum input that will just turn the diode on. Yeah, the current is still zero, but when the input voltage slightly get beyond the input minimum, increased than the input minimum, there will be a current flowing through the diode, positive current. Okay, so let's call this point 1. At Vn is equal to Vn minimum, the diode will just conduct. I mean, the operating point is at 1. Okay, and at 1, Vd is equal to 0.7, and Id still 0. When Vm would increase beyond V minimum, there will be Id, positive Id. Okay, good. So let's go to the circuit and see what is the condition of the circuit at that point. So you have here 0 current, ID is equal to 0. So at operating point 1, since ID is equal to 0, so I is equal to I1. But Vd is equal to 0.7. If this is ground here, and you have here 0.7, so this point or this node is 0.7 because the voltage drop is 0.7, so this is larger than this by 0.7. If this is ground, and you can assume as a ground anywhere, that's fine. So this is 0.7. I is equal to this point minus this point over R2. Now V input is V input minimum, remember. So I is equal to Vn minimum minus this point, which is 0.7 over R2. And what is I1? I1 is equal to VR1 over R1. What is VR1? This is VR1 here. This point minus this point over R1. This point is 0.7 minus 0 over R1. Or basically the voltage drop on the diode, which is known now, because it's on, just on. is 0.7. So 0.7 over R1. Good. Now our equation has only one unknown, which is V input minimum. So Vn minimum minus 0.7 over R2 equal to 0.7 minus 0 over R1. So Vn minimum will be equal minus 0.7 equal to 0.7 R2 over R1. So Vn minimum equal to 0.7 plus 0.7 R2 over R1. So the minimum input that will turn the diode on is actually dependent on the values of both R2 and R1. Okay, it's not an arbitrary value or independent value. No, it depends on the circuits. Now, we just said that here, if whatever the V input, if R1 is 0, the diode will be off, right? Now, if we put here R1 with 0, what will happen in that equation? What will be the input minimum? Guys, please repeat. Yes, infinite voltage. That's right. Yeah, because basically you put a short circuit. So whatever the value of V input, this is what I'm saying. Whatever the value of V input minimum, the diode will never turn it on because it has short circuit in parallel. So the voltage drop across the diode is always 0. So whatever the value you have in the input, this will never turn the diode on. Okay, that's very good catch. Now let's go, before going to number B, I want to just explain what will happen exactly without even math, okay? Because we can drive this, by the way, without using math, okay? So let's see what will happen exactly before, at the moment, or before the moment the diode will turn on, okay? So let's even make another, this thing here. It's really useful. Draw the circuit again. This is R1, this is R2, and this is okay, the input. And this is our diode. Okay. Okay. I will give some, some values. So let's assume that V input is equal to -1. It will be on or off. Basically, it will be off because this is reverse, right? So at -1, this is off. No current flowing through the diode. It's basically infinite open circuit. Okay. So the voltage here, which is VR1, is basically V input all the time multiplied by R1 over R1 plus R2. Okay? All the time. So assume that R1 is equal to R2, whatever the value is, 1 kilo, but the value is not, it's not a matter of concern. So in that case, VR1 equal to -0.5 volt. Is that an enough voltage or a voltage that turns the diode on? No, of course. At that particular example, VD would be -half a volt. So it's off. It's really off. Let's assume the input is 0. Again, this guy will be off, the diode. And again, no current is flowing through that. So just like a series. I mean, R1 and R2 is just a series. So it's a voltage divider again, just like this one. So in that case, VR1 is equal to 0. 0 multiplied by anything is 0. and VD is also 0. And that's not enough for the diode to conduct. Another example. Let's change the color again. Okay, black, that's fine. V input is equal to 0.7 volt. Just, 0.7 volt. The diode will be off. I will show you why. But let's just keep with this. The diode is off. So again, the current is 0. And again, R1 and R2 are just in series because they have the same current. Voltage divider again. So VR1 in that case 0.35. Remember, they are equal in values, as I assumed. This is equal to VD. So it's again off. Yes, it's forward. It has a positive voltage, but less than 0.7. It will not conduct at 0.7. How about 0.8? How about 1? It will be off. And again, with voltage divider, VR1 is equal to half a volt. It's still less than 0.7. So again, this is equal to VD, less than 0.7 is still off. Okay, let's continue. Let's go up. So with 1, it's not conducting still. Now with V input equal to 1.4, and both resistors are equivalent. This is the current, this is the voltage that will just turn on the diode. And I mean by just turning on the diode, I mean the diode will just be operating at that transition point here. Why is that? Basically, if we assume it's a transition point, again the current is 0, again the voltage divider holds, so VR1 will be 1.4 R1 over R1 plus R2. They are equal in values, so this is just a half, so 0.7. Remember, the current is 0, and we have here 0.7, so we are working, or the diode is working in that, point here. Now with V input equal to, for example, 2 or 1.5, well, let's say 1.5. Okay, now the current, the diode is really on. Okay, and the voltage will be constant at 0.7, and any and there will be a current, okay, and they are not in series anymore, and we need to do some analysis. Okay, so basically, and this is the input minimum without making any math. Okay, so basically in the beginning, this guy is off. Assume that this guy is coming from minus infinity until infinity, and the changing. Okay, so with all negative values, the diode is off. Okay, voltage divider. With some positive values of the input, still voltage divider holds, still the diode is off. Okay, until you have a voltage input that is capable of providing 0.7 to R1. At that point, the diode will be just on the transition point. Current is 0, voltage is 0.7. Okay, without doing all of that math. Now, let's go to B and see. This is clear, guys? Any question? Don't be shy. Any question? Now let's do to B. Let's go to B. If R1 is equal to R2 equal to 1 kilo ohm, find IDVD. Okay, and V input is equal to 1 volt. V input is equal to 2 volt. So what we're gonna do basically, in A, we get the input as a function of R1 and R2, just to calculate it. Vn minimum 0.7 plus 0.7. R1 is equal to R2 equal to 1 kilo ohm. .4 volt. So any input voltage less than 1.4, the diode is off. At 1.4, the diode is on the transition point. VD 0.7, ID is 0. Any input larger or greater than 1.4, the diode is on and there is current and VD is constant equal to 0.7. That's easy. So in number 1, he said that at input equal to 1 volt. This is less than Vn minimum. Diode is off. Very, very straightforward. No assumption here, by the way, because you know what is the minimum input that will definitely make the diode on. So there's no assumption. Just compare with the input voltage minimum. ID is equal to 0. R1 and R2 can be considered in series because that is just open circuit. So VR1, for example, is equal to V input, I'm sorry, 1 multiplied by R1 over R1 plus R2 is equal to half a volt. And that's actually a check for you because the input should be less, the VD should be less than 0.5. And with number 2, with Vm is equal to 2. This is larger than Vm minimum. Diode is on. Vd is equal to 0.7. ID should be larger than or equal to 0. Positive, I mean. And in that case, they are not series anymore. You should solve the circuit. Okay, so let's go up here. It's easy still because you know that, guys, too. You know, here we have 0.7 because this guy is on right now. So you can determine easily what's I. So I is equal to Vm minus 0.7 over R2. V input is 2 minus 0.7 over R2, which is 1 kilo ohm. This is 1.3 milliamps. You can determine also I1. It's equal to VR1 over R1. And VR1 is just in parallel with the diode, which is 0.7. So 0.7 over R1, which is 1 kilo ohm, 0.7 milliamps. I is equal to I1 plus ID. Because it asks for, in the question, it asks for ID. This guy is 1.3, this guy is 0.7. ID is our unknown. ID from this will be equal to 0.6 milliamps. And as a check, it's positive. So we are on the right path. Okay. That's a very nice example. Okay, because it gives you some vision about what's happening really before and what is the requirement for the input in order to turn on. And by the way, this is something that you can, to avoid having assumptions and prove or disprove. Because now you determine V input, what is V input minimum. If you have any input, you know for sure. Just compare it to V input minimum and you will know for sure if the diode is on or off. No assumptions. Just checks that, yes, the numbers are right. Okay, guys, any question? Okay. What is different between that circuit and the previous circuit? There are two differences. Any idea what are the differences? First of all, look at the symbol. Is this a normal diode or a special type of diodes?
It's a Zener diode.
Yes, and it's in reverse. So if we compare this to the previous circuit, this guy is reversed. Not reversed. I mean, if the input is positive, this is reversed. Okay, because maybe I said that this is the polarity of the battery, but maybe the value of the battery is -2. So you must change it from that way to that way. Say 2 here. Okay. It's a little bit tricky here, because we must say what is the value of the input. But let's assume the input is positive. Okay. So the polarity is correct. Then this is a Zener diode connected in reverse. And we know that Zener diodes can work in reverse. So let's draw first the characteristics of Zener diodes. Similar to normal diode, except that we break down at some value here, at V breakdown. And this is 0.7. Good. So when I draw a Zener diode in that way, it's reverse. If the input is of course positive, okay, but can conduct. It's not all the time off. No, it can conduct at that point. And this is actually what's required in part A, or question A. Find the minimum input voltage, which turns the Zener into breakdown. It will be exactly the same as our previous example. Exactly. Actually, I did the previous example in order for you to understand this one. So we need to determine the minimum input voltage that will just turn the Zener into breakdown. I mean, it will be working at that point here, just at breakdown. So in A, the Vn min, but in reverse, remember. We are talking now about V input minimum that is connected in reverse to the Zener, and that guy will just turn the Zener into breakdown. By the way, breakdown is an on state. So this is on. This is also on, but reverse it. I mean, the polarity, both voltage and the current are negatives. Here, both in this part, both current and voltage are positives. And in between, it's off. Good. Same as what we did with the previous example. We want the point at which the Zener will be just a breakdown, which is 0.1. So this will just turn the Zener into breakdown. At that point, at 0.1 here, VD is equal to minus V breakdown. To avoid any confusion, whatever the value it gave you in the question, okay? Because you find in some books the breakdown voltage is minus 100, minus 10. It's some other books. They mentioned that the breakdown voltage is positive. So he meant the same. They both mean the same. Okay. So to avoid this confusion of polarity, just write VD at that point when we are breakdown minus whatever the value he gave you in the question or the textbook you have. Okay. And the ID will be as a magnitude larger than or equal to 0. As just a value, ID is less than or equal to 0. It has some value but negative value. Was what I'm just trying to, avoid the confusion of polarity, minus or positive, because in reverse we have negative and negative currents and negative voltages as well. Good. As I draw here, I draw the Zener diode. So okay, what I usually do when I know that the Zener is working in the breakdown region, I usually assume the voltage in that direction from B to N. Remember, VD usually we do it in that way, from N to B. And the current is flowing from N to B, IZ, and I call it IZ. This is opposite to the one that we usually do from B to N. And that way, ID and VZ, if we are working in the breakdown region, IZ and VZ should be positives. Just to avoid the confusion. So I assume, other names, symbols for ID and VZ. But in that particular question, he gave you such polarities. He gave you that VZ is going upwards, IZ is going downward, and you must find these unknowns based on the directions he gave you in the example or the problem. Good. And we know such polarities, IZ is minus ID. So in that particular operating region, IZ is larger than or equal to 0. And VZ is minus VD. It's opposite to it. So it should be equal to V breakdown as a positive. Just to avoid the confusion. So these are the original directions for VDI and ID, and these are the directions he gave you in that example. So with these directions, the red ones, the value should be positive. If you play with the original directions that we usually assume for the diode, normal diodes, okay, that's fine, but they must be negatives while you are in the breakdown region. Okay, that's good. That's very good. Now we want the input voltage minimum that will just turn the Zener into that operating region here. At which, sorry, this is some problem here. So in breakdown. But at point 1, the voltage is VZ and the current is equal to 0. So the voltage of the Zener is equal to VZ and the current is equal to 0. Now we do the same trick as the previous one. And we'll ask the same question. If R2 is 0, is just shorted, does this guy will go into the breakdown region? Any idea? What will be if this is shorted? If R2 is shorted, is 0, what will be the value of the voltage drop across the Zener diode?
It would be 0.
Of course, and it will not go. It will be here. And this point here has a current of 0 and it belongs to the off region. If the V input, for example, is if V Zener, the breakdown voltage is 10 and V input is 5, is that also a good input voltage that will turn the Zener into breakdown? No, because to go to the breakdown, the input voltage should at least be equal to, at least in some circuits, equal to the breakdown voltage. If we assume that V zener or V breakdown, I'm sorry, V breakdown is 10 and the input voltage is 5 and reverse, yes, it's reverse, but it's just only 5. So this will not turn the zener into breakdown. Good. So at the breakdown, if this is 0 here, the voltage will be VZ, which is equal to the breakdown, but the current I zener equal to 0. So R1 and R2 is just, voltage, they are just a series. So since IZ is equal to 0, so R1 and R2 can be considered series. And VR2 is equal to Vn multiplied by R2 over R1 plus R2. At the same time, since the voltage on R2 is equal to VZ, since they are in parallel, so this guy is equal to VZ as well, or the absolute value of the breakdown voltage. So Vn is equal to Vn minimum, by the way, I'm sorry, the minimum input required to turn the zener into the breakdown, equal to Vz R1 plus Vz R2 over R2, equal to Vz, if we distribute this guy with this guy here, so this with this will give us Vz plus this with this Vz plus R1 over R2. This is exactly what we get with the diode. We get with the diode, remember, 0.7 plus 0.7 multiplied by R over R. The one not in parallel over the one in parallel. This is the same what we have here. Exactly the same. And that's obvious. For the first one, we need at least 0.7 plus something, right? Here again, we need at least Vz plus something, I'm sorry, this is multiplied, plus something dependent on the ratio between the resistances. Good. So this is the input minimum that will turn the diode on. Now let's do B. For B, if R2 is half kilo ohms, R1 is 1 kilo ohm, find IZVZ with 3 inputs. Okay. So let's do B. Okay. R1 is equal to R2 1 kilo, R2 is 1 kilo ohm, R2 half kilo ohms, and okay. And V zener is 10, by the way. Oh. V breakdown is 10. Before anything, we calculate V input minimum. V input minimum is equal to Vz plus Vz R1 over R2 equal to Vz is 10, and the R1 is 1 kilo ohm, R2 half kilo ohms. This is 10 plus this is half, this is 2, 20 equal to 30 volt. So although the breakdown voltage is only 10, we need 30 voltage at the input in order to just turn the zener into the breakdown. And why is that? Because the resistance that is in parallel with zener is actually half of the other resistance that is just a series with the battery. So it always receives half of the voltage that is going to the other resistor in series with the battery. That's why we need more and more voltage on the input in order to turn the zener into the breakdown. So in I, it become easy now. With Vn equal to 20, that's basically less than 30 volt, which is V input minimum. That's required to turn the zener into breakdown. So zener will be just reverse and off. Will work in that region here. Reverse, yeah, it's reverse, but off. It's not breakdown. Not breakdown. If it's not breakdown, then ID or IZ. Yeah, let's be consistent. IZ, which in that case equal to ID, because yes, they are opposite in direction, but you know, 0 minus 0 is 0. Is 0. So R1 and R2 can be considered series. So VR2 yes, the one in parallel with the zener, equal to V input, which is 20 multiplied by half, or R2 is half, yes, over 1 plus half. So this is 20 over 3. That's 7 point something, 7 point, you know, 33, something like this. Let's do it that way. Okay, which is basically less than V breakdown. And that's your check. Since you say it's off, so the input, the voltage across the zener should be less than the breakdown voltage. If you work with the original polarities, ID and VZ, those guys here, if you calculate, VD will be minus 7.3. It's not minus 10. So it's really not in breakdown. Okay, number 2. Vn equal to 35 volt. That's bigger than V input minimum, or greater than V input minimum. So definitely the zener is in breakdown. And with that, V zener is equal to 10 volt, which is the breakdown voltage. And I zener should be larger than 0, because it will be equal to 0 only if V input equal to V input minimum. But this is larger than or greater than V input minimum. Okay, how to calculate this is very easy. Now VR2 is equal to VZ because it's in parallel with the zener. And this is so IR2 or I2, I name it R2, equal to 10 over half a kilo, 20 milliamps. I, which is flowing in R1, is basically equal to Vn minus Vz over R1, 35 minus 10 over 1 kilo ohms, I'm sorry. This is 25 milliamps. But I equal to IZ, the moment of truth now, plus I2. Okay, so this is so IZ equal to I minus I2. I is 25 milliamps. I2 is 20 milliamps. That's positive 5 milliamps. That's correct, because we assumed the zener current flowing from N to B. So it should be positive in breakdown. If you assumed it with a regular polarity, I from B to N, it should be minus 5, which is the same, which is also correct, because we are working in the breakdown, So with the regular polarities, the voltage and current are positives, are negatives. But with this, new polarity, IZ and VZ, they are both positive. Okay. Now, the last part, which I will not do it with you, it's actually a homework, is to solve the same, but now V input is minus 2 volts. I will not do that with this is your homework. So this is homework. Okay. Homework 5, I think, whatever. So try to do that by yourself. The first question is, this is forward or reverse with V input equal to minus 2. Forward, yes, it's not reverse anymore. And in forward, we have a new story here. Since it's forward, we are here. Forget about this. And forget about the input minimum. You can't make the comparison anymore. So to give you a hint, you need to know or to determine the minimum input voltage required for the zener in forward in order to make it conduct in forward. Then you can compare. Okay? And you can, basically make something easier just, to guess if it's forward or reverse and try to, offer on, I'm sorry, and offer on or on and try to prove or disprove your assumption. You can, for example, assume it's on. So the diode voltage would be 0.7, okay, from N to B. And the current should be positive from B to N, okay? So this will be for you, okay? Whatever you choose to do, whether to determine the minimum input required for zener to conduct in forward or assume some assumption and disprove or prove it, it's up to you. This is your homework, okay?